So yeah, we finished the maths bit, yeah. But let me see what we're gonna do today. What do you want to do today? Let's start out with any question you have first.
Not really. I don't have much.
Yeah, much questions. Okay. You okay with the odd function and the even function already? Yeah.
Yeah.
Okay, cool. So no question from your side? Nothing?
No.
Okay. How's the application process going at the moment?
I think I finished my first draft. Now I'm
Okay.
trying to.
How about the TSA? Have you registered?
Yeah, already. Already paid and everything already.
Was there confirmation already from GIS?
Yeah. Already
Okay,
emailed
cool.
me the receipt.
All right. Just the section A, yeah? Have you
Yeah, the first.
Have you had a chance to look at them at all? Because that is to be taken in November, like in between your A levels. So you should probably take a look at them. I wouldn't set any work for the next few weeks in your A level. You just go through those TSA, and the sample papers have got the like the ABCD options, the answers online as well. So then you can figure out like where you went wrong and how you went wrong. Okay.
Yeah.
They are actually quite important to decide because first of all, your O-level score, then your predicted score, your AS score, your TSA score, and then your interview score is the most important one. But all of them is gonna play a role in whether you get a place or not. So the TSA does differentiate between people who can think critically or who cannot, because multiple choice is not easy. If you can get all of them correct, it really proves that you are willing to think critically, which I'm sure you are able to. Okay, cool. Yeah, shall we get started? Yeah. We're just gonna be doing miscellaneous thing partly because I forgot about it all, and then like I had a late night today, this morning, so I didn't really come prepared. But anyway, can you write me balanced redox equation when you react acidified iron 2 with potassium manganate 7, just manganate 7. You get the question? Can you write a balanced equation? A balanced ionic equation between manganate 7 ion and acidified iron 2.
Acidified iron 2.
Yeah.
MnO4 minus plus H plus Fe2 plus. Fe2 plus wants to get oxidized to Feg plus. And let's see. That means MnO4 minus gets reduced to MnO2.
Yeah. What's the problem?
I'm not sure what MnO4 minus get reduced to.
Okay, the MnO4 minus is the usual manganate you use in a titration, right? In this kind of titration, redox titrations, the MnO4 minus is very much likely to get reduced all the way to Mn2 plus. That's the colorless pinkish solution that you normally see. MnO2 it's the charges are balanced. It's ionic solid, and it's actually not very soluble in water, unfortunately. The MnO2 is a normal catalyst for If you have a piece of liver, and then what was I gonna say? Liver is like contains the enzyme that can naturally catalyze hydrogen peroxide decomposition into water and oxygen. So if you have just hydrogen peroxide on its own, it will bubble because it will release O2 slowly. You put a piece of the human liver, well, not just human liver, like animal liver. There's the enzyme that will spit out, and then you get that effervescent fizziness. On the other hand, you can also use an inorganic catalyst such as MnO2, and MnO2 happens to be a really good catalyst for that. It's a black powder solid kind of thing. Usually in qualitative analysis, if you're given a black powder added to something colorless and then you get fizziness, most likely what you added is MnO2, and most likely the fizziness is O2 because there's hydrogen peroxide decomposition. But not you won't be getting MnO2 when you do this kind of redox reactions. The Mn4 minus go to Mn2 plus. So will you be able to balance the equation for me then?
Yeah. So MnO4 minus plus H plus Fe2 plus. The overall charge is 2 plus. And then for the product side, I got Fe3 plus Mn2 plus, but then the overall charge is 5 plus. So that means I haven't balanced the charge yet. And there's also the H and O missing from the product side.
Mm-hmm.
So that means
Yeah.
I minus and need to balance hydrogens. 4OH minus, 4H plus, and then charge is not balanced. No.
So how?
We need electrons, I'm guessing.
But if it is a redox reactions, then it's supposed to be balanced out, right? Oxidation balanced out by reduction. So how?
Formation from water instead of OH minus and that means here needs to be 4 to balance the oxygen and reactant side. So for H2O 8H plus, but then
So how?
plus 9.
Did you how would you normally do this if you're given this in A level? How would you normally go about approaching this question?
Data booklet, but
booklet in the interview, unfortunately. There's
yeah.
to catch people up. Like, can you or can you not? Okay, let me teach you a short trick. The shortest cut for it is come up with your own half equation. So you will go to the data booklet and then get the data for each oxidation or reduction equation, and then you combine them. Do that manually, and then you'll be able to get the full equation much easier. Because if you can get the half equation, excuse me, if you can get the half equation correct, Then you just have to add them together just like we would normally do the data booklet. So get the half equation first.
Okay. Fe2 plus, wait, Fe3 plus E minus electron gives Fe2 plus.
Okay, so there's your reduction.
And then
So that is your oxidation. You're supposed to write as oxidation because you're reacting acidified iron 2, you see. So it's iron 2 going to iron 3. Yes, it will look like iron 3 going to iron 2 in a data booklet, but in reality, the MnO4 minus is getting reduced, so the iron 2 is actually getting oxidized. Hello? Are you with me?
yeah.
Very easy. Just write Fe2 plus, go to Fe3 plus electron.
Fe2 plus gives Fe3 plus and
Yeah, there is your oxidation, right?
yep, that's what I wrote.
Okay, now write your reduction.
MnO4 minus plus
You gotta be able to do this faster, yeah?
H plus plus E electron Mn2 plus and water. And then need to balance the charges. So 4H2O 4H2O's 8H plus. So the charge on the left hand side is +6, the right hand side is +2. So that means the left hand side needs to -4, so +4 electrons.
Wait, how many electrons?
Wait, no. Wait. Exclude the electrons, then it'll be +7, 5 electrons.
Sorry, so for the manganese, how many electrons? For the MnO4 minus, how many electrons does it need to get?
5.
Okay. So are you able to give me the full balance equation now?
Yeah. MnO4 minus plus 8H plus 5 Fe2 plus gives Mn2 plus 5 Fe3 plus 4 water molecule.
Yeah, that's fine. Can you repeat the exercise for me, but with dichromate 6 as the oxidizing agent, acidified dichromate 6.
Okay. Dichromate 6. Acidified dichromate 6. So
Yep. Without the acid, you will not get the redox, you see. So that's why it's very important to have all this acid in there because otherwise the redox will not work. And if you have acid don't exist as H plus unless you have water. Bases don't exist as OH minus unless you have water. So the water comes around because there's H plus. If you have H plus, you have water. If you have OH minus, you have water. Definitely. Yeah.
Oh yeah. Chromium wants to reduce to Cr3 plus though.
Okay. So now that you get the hang of it, you should be able to give me the chromium one a bit faster then.
Cr2O7 plus H plus electrons because it wants to reduce. So gets 3%. And there's CRs on the sides, so the product to CR. some oxygen. That means we have 7 water molecules. And for left-hand side, the overall charge on the left-hand side, excluding the electrons, would be 12 plus positive 12. And then there is plus 6 on the right-hand side, so that means we need 6 electrons to balance the charges. And then for the oxidation, wait, if direction also using iron. FeG plus. So Cr2O7 plus 14 H plus 6 Fe2 plus gives Trg plus 6 Fe plus 7 water.
Done? Hello? Hello? Are you there? Hello? You are cracking up. Are you there? Can't hear you at all. You still there? Wi-Fi very bad on the side. Hello? Are you still there?
Yeah, so
So yeah, so have you gotten me the? Oh no, I can't really see because the thing is really blurry. Why don't you just tell me that? By the way, again, you cannot use this Skype connection for your actual interview. This will not do. You can do it in school where the connection is a lot faster actually. Tudio will help you set it up. Can you hear me? Hello?
yeah, sorry.
Okay, cool. You can put the paper down, it's fine. Did you get so there should be 14H plus? Hello? 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 Nope, this can't get through at all. I totally lost you there. Hello?
Sorry.
Yeah, the connection is.
Okay, there we go.
What did you change? Because I don't know. Yeah, but essentially, yeah, everything was hanging. Just the audio didn't go through. But anyway, so you get the idea of the redox now, yeah. So this thing can
Yeah.
come out of the blue, and the thing is that no data booklet. So what to do? This kind of thing. So this shows that any competent chemist should be able to write a half equation. And from the half equation, then it shows can you balance equation quickly? Can you then charges and atoms? And if you can do half equations, you can do oxidation reduction, then you should be able to combine them and get the full equation confidently and very quickly as well via this method. Instead of writing the whole equation and trying to balance your stuff out of it, which is quite a hassle, yeah? So now you know. Obviously in A-levels, you can resort to the data booklet, but there are times when you don't have data booklet and then, yeah. Cool. Happy? Yeah, shall we move on to a bit of organic then?
Okay.
I will. Do you want me to send to your phone, or I think it's better if I send you to your phone. And then hang on, I'm just gonna open up my WhatsApp and send you the reaction scheme. So it's a simple reaction scheme. Just have a look at it, and then think about what are the compounds, and then rationalize it to me. Have you received the file?
Sure. Not yet.
I sent it to you. Yes, I did. Yeah.
Oh yeah, I got it.
Cool. All right. So, so can you tell me anything you know about the first structure on the top left? Like, what are the kind of functional group you can see there?
Phenol group, the alcohol group, and then that's the double bond. Oh,
No, it's not a double bond. Or look at the connectivity.
wait, no,
If
that's not double bond.
if they want
Ether?
if they want it to be a ketone, they will have draw it as a ketone, or they will put the O as a bracket. But the fact they draw it like that is because that oxygen is bent 104 degree, because it's got two single bond, one to the aromatic carbon and one to the methyl carbon. This is called an ether, ether.
Mm.
It's not really in the A-level syllabus, but it's just another functional group. So it's an ether group. Okay.
Yeah.
But you shouldn't be confused by it. It's not a carbonyl. Yeah. Okay.
Okay.
Cool. So from there, do you know SOCl2?
Thionyl dichloride.
Yeah. Okay. Do you know what it does? What do you think it does to this thing?
Nucleophilic substitution of the OH group.
Okay. And it becomes what?
Halogenoalkane.
Okay. Do you want to just draw me the skeletal formula, like of compound A then?
Yep.
So you're right. It has done a nucleophilic substitution reaction. It has replaced the OH with a Cl. So basically, it chlorinates alcohol. It chlorinates carboxylic acid as well. So it does nothing to the ether group. It just chlorinates the OH, right? Cool. All right. It's nice and easy. Now the next one is not something you are familiar in A level, so I'm gonna throw something at you. Okay. So
Yeah.
magnesium is a reducing agent. Do you agree?
Yeah. It's
Okay.
a metal.
Yep. And then this is the start of something called organometallic chemistry, which is my area. Okay. The founding father of my field actually worked with this reaction, this particular reaction actually. So when you have a halogenal alkane, not just halogenal alkane, or even like acyl chloride or anything with a reactive carbon chlorine bond. Okay, this magnesium can act as a reducing agent. If it acts as a reducing agent, what happens to it, sir?
It gets oxidized.
Okay, so this is magnesium 0. It will become magnesium 2. So in the reaction in situ while it's stirring, okay, while stirring magnesium, the magnesium itself will slowly become Mg2 plus, and then it will insert in between the reactive carbon chlorine bond. So you are getting kind of like a covalent bond between the carbon and the magnesium. And you're also getting like a covalent bond from the magnesium to the chlorine. You can think of it as like
Yeah.
covalent, but in reality, it's actually very polarized. So
Okay.
it's not 100% covalent, it's not 100% ionic. It's very polarized. Mg2 plus, highly charged, relatively small size cation, quite a high charge density cation, and therefore it polarizes the bond a lot. Yeah, okay. But what it does is you have converted a halogenal alkane, which is what is the polarity on the carbon chlorine bond?
Carbon delta
Originally,
plus,
originally,
Cl delta minus.
why is that? Why do you say that?
because Cl is more electronegative than carbon, so it pulls
Okay.
the electrons. So
Okay. Cool. All right. So what I just told you is that the magnesium will act as a reducing agent. It will insert in between the carbon and the chlorine, reactive carbon and the chlorine, but it doesn't do this with halogenoarine, partly because halogenoarine is not easy to hydrolyze for the same reason. It's not a reactive carbon-chlorine bond. Okay.
yeah,
So this is a reactive halogenoalkane, carbon-chlorine bond, magnesium insert in between. So if you now have a carbon bonded to magnesium, bonded to chlorine, what is the polarity on the carbon now? So if you have a carbon magnesium bond, how is the polarity like? Suggest and why?
let's see. Magnesium is Mg2 plus cation.
Are you confused or do you understand what I'm asking you?
Yeah, what's the polarity on the carbon?
Yeah. So imagine like it is quite ionic, but there is covalent character. So in that covalent bond, that because now the magnesium is inserted in between the carbon and the chlorine, so now you have a carbon magnesium chlorine covalent bond. So what is the polarity on the carbon magnesium covalent bond right now?
Magnesium is electropositive, so that means it would pull electron towards itself. So
Wait,
that means,
hang on. Electron positive means you will pull electrons towards yourself.
I mean, a push is, but then it's 2% actually.
So if you have a carbon magnesium bond,
If magnesium wasn't charged, then it would be electropositive, but then this one is Mg2 plus.
sorry,
So
you say it will be electropositive. So my original question still remains. If you have a carbon, single covalent bond to magnesium, and these are organometallic compounds. Yes, magnesium can form compounds like this. And so what is the polarity like? Which one is delta plus, which one is delta minus?
carbon would be delta minus then, because carbon is more electronegative than magnesium.
Yeah,
Magnesium lies
essentially,
at
yeah.
the left side of
Yep.
periodic
In
table.
fact, it doesn't matter. I could give you a carbon barium covalent bond. It's not going to be very strong because barium is very big, and then down that group, it becomes less polarizing and things like that. So it becomes harder to form organometallic complexes carbon barium bond, but it is possible. And but yeah, I mean, the polarity wise is that if you can think of a schematic, okay, so you will have like electronegativity going increasing from left to right, let's say, and then you will have like carbon in between, okay,
Yeah.
things like this. Can you see that?
Yep.
Just a normal en short for, so left to right increase. Okay, if carbon is there, do you mind just continuing for me? Where do you think metals will be and non-metals will be in general? Just let's start with general. Do you think metals will be on the left hand side or right hand side?
Metals will be on the left of the arrow.
Okay, metals in general are electropositive, right? Metals like to gain electrons. Partly for the same reason, metals prefer to lose electrons. They are electropositive, and therefore they will actually prefer to be on the left side. So the metals will occupy this area. Therefore, if you have a metal carbon bond, metal carbon covalent bond, you will always have a delta negative on the carbon because metals like to.
Yeah.
Make sense? This is lesson 101 on organometallic chemistry because what have we done? We started from organic compound. Now we chuck a metal to it, and now you have a metal carbon bond, metal carbon bond, metal organic bond, organometallic,
Yeah.
organic and metals. This is the boundary This where there's no more boundary between inorganic and organic. Okay, can you quickly Google me a structure of chlorophyll? You know, the green pigment in leaf.
Okay.
I know you don't do biology, but you must have heard of chlorophyll.
Yeah.
Have you got a structure in front of you? Do you see it?
Yeah. I
So what can you tell me that is interesting about chlorophyll? About the structure?
There's magnesium in the middle.
There is not a magnesium metal, it's a
I
magnesium ion. Can you see
yeah.
that? It's a Mg2 plus. Yeah. Okay.
Yeah.
Can you see the Mg2 plus is forming a complex? So this is actually a complex ion. And
Yeah.
what you have is that you have that surrounding thing and it's coordinated to Mg2 plus. So what you have is that do you know why it's Mg2 plus? Why not Mg0?
Mg2 plus.
Yeah. Can you see the four nitrogen? Are the four
Yeah.
nitrogen the same?
No. Two
Why
is
not?
negative.
Yeah. So two of them have negative charges because they only have two covalent bond, right? So that
Yeah.
means it has one extra electron that form that dative covalent bond to the Mg2 plus. Happy? And that's why the
Yeah.
charges balance out as well. Okay. And then the other one is using just the lone pair to form the dative covalent bond. Okay. So what do you think is the geometry like at the magnesium 2 plus based on that structure?
Geometry. Okay. Nitrogen, carbon.
No, I don't care about the carbon. I'm looking around at the magnesium. So what's the geometry like at the magnesium and why? So you have four covalent bond, right? So two are normal covalent bond, two are dative covalent bond. All right. The normal covalent bond is the one from the ionic nitrogen. Yeah, because it's a normal covalent bond. The dative covalent bond is the one where the nitrogen uses the extra lone pair because there's
Yeah.
no charge on the nitrogen. Okay. So when you have four bonding pair and zero lone pair, can you tell me what geometry can you have?
It's just square plane. With
Um,
two lone pairs.
how many lone pair you said? Are they lone
No,
pair or magnesium?
there's no
The
lone
M,
pairs.
yeah, because it's all inertial electrons. Yeah, magnesium third period. Yeah, group two. So
Tetrahedral, because it doesn't have any lone pairs and just four bonding pair.
yeah, so what's the geometry like? What do you think? Suggest. Any?
Geometry.
What's the shape in the Mg2 plus? This is a real compound, right? What you see in leaves around you.
Yeah.
So this is another organometallic compound actually.
Tetrahedral.
Sorry, what shape did you suggest it was?
Tetrahedral.
Okay. Um, in reality, I torn between like tetrahedral, but then they don't draw it like tetrahedral. Okay, I'll tell you it's square planar. Okay, my next question is, do you know what my next question is?
Why is it a square plane?
Yeah, or rather, in other words, why not tetrahedral? Why not?
Because
Suggest. It's got something to do with the structure. Mm-hmm.
the carbon and the nitrogen lies on a plane. Something.
Yeah. So can you imagine like if you have to force it to be tetrahedral?
Yeah.
Yeah. If you have to force it to be tetrahedral, it's not gonna like it. So yeah, I mean, if you have a free ligand, if you have free ligand like chloride, yeah, not that you will have just four chloride and the magnesium, but I'm just saying if you have chlorides like four ligands on the thing, it can either go square planar or it can either go tetrahedral. But
Yeah.
preferably things would like to go tetrahedral because of VSEP. I remember in a square planar you only have 90 degree between the bond pair and the bond pair.
Mm.
Square planar is not as good as tetrahedral because your bond pair are actually 109 degree away from each other. The further they are away from each other, the lesser is the repulsion. That is the basis of the valence shell electron pair repulsion theory. I can't even see your face right now, and your voice are cracking. The next time we do this, can you find a room which has got a slightly better connection? Yeah,
Yeah.
okay. This one is getting worse and worse. But anyway, cool. Do you get the idea now? Like, so organometallic complex can be there. Um, do you know that there are many natural compounds that contain organometallic? They are actually essentially organometallic complexes. So things like hemoglobin. You know your hemoglobin molecule. Why don't you
Yeah.
look up heme group HAEM hemoglobin? Okay, just look it up.
Okay.
So hemoglobin is a protein, yeah, okay. So protein is very big, but within, if you talk to your brother, within the protein itself, there are certain active sites. Those active sites are active doing what they do because they have transition metal center. Not just transition metal center, they have metal center. What's the metal center capable of? Metal center, free vacant site allows coordination to it,
Yeah.
and therefore you can do a lot of chemistry on it. And that's where the term biochemistry, biological chemistry, what else? Well, that's where there's no more boundary between chemistry and biology as well. So these are the kind of things like you might have read up, well, now you know that you could be interested, you could be keen to find out more about these things. Do you have the structure of hemoglobin now in front of you?
Yep.
So I'm looking at Wikipedia and then I'm looking at the structure. Do you see similarity between the backbone around the iron 2 and the backbone in the chlorophyll just now?
Yeah.
Okay,
Yes.
it's again the geometry at the iron 2 there is actually a square planar, partly because of that constrained planar ring structure. Yeah. Okay, so as a matter of fact, it's square planar there. But what actually happened is your oxygen molecule can bind above and below the plane
Yeah.
because free coordination side, right? Okay. And then we talked about carbon monoxide last time. When you have a carbon monoxide molecule, it's polar because carbon and oxygen have different electronegativity, right? The polarity like at carbon monoxide?
What? Sorry.
What's the polarity of the bond in carbon monoxide like?
Oxygen delta plus, carbon delta minus.
Yep, so it's actually because of the dative covalent
Yeah.
bond, right, from
Yeah.
the
Yeah.
oxygen towards the carbon, and therefore it's actually the carbon that will bind to the iron 2 center, replacing the non-polar oxygen. So in addition, that's why like CO is very dangerous to us because it's polar. O2 is non-polar. The CO would love to displace O2 anytime because of the ionic interaction with the hemoglobin center. And you got a free coordination site there above and below the hemoglobin molecule. The rest of it stays intact. It doesn't do anything with oxygen or CO. It's just the iron site, the iron 2 site is quite important. Yeah. Cool.
Yeah.
So those are just two examples of organometallic complexes. If you look up online, there are heaps of very important stuff. Actually, that's the next one. Do you know vitamin?
Yeah.
Okay.
Vitamin.
Yeah, look up vitamin B12. You'll be surprised by this.
Vitamin B12.
Yeah. Vitamin B12 is again a protein and it's got a structure. And within the structure itself, you will see if you type vitamin B12, have you got the structure? I'm looking at the
Yeah.
Google image actually. Ooh, what do you have there?
There is a compound CO plus. There
Do you think
is
it's cobalt plus or cobalt 2 plus or cobalt 3 plus? Which one?
um
What do you think?
cobalt 2 plus. Or cobalt.
Mm, sorry, can you finalize what you're gonna say?
Cobalt 2 plus.
Cobalt 2 plus, and that's correct because the R group itself is a R minus. It's got a carbon. Why do we say it's a R minus? Because cobalt is a transition metal. It carries the electropositive center, therefore it's the delta plus. And then the R group, the carbon itself is a negative group now. Happy?
Yep.
Okay. And then the other thing is that you have one of the nitrogen with two covalent bonds. That's why that is another source of N minus, right? So cobalt 2 plus. Can you tell me the electronic configuration of cobalt 2 plus?
Cobalt 2 plus.
Oh, well, hang on. That's not fair. Okay, sorry. Yeah, that's not fair. Because you're not expected to remember up to the transition metal. Okay, never mind. I will skip that question. But what's the geometry of the cobalt here?
Let's see. Nitrogen and the carbons are on the same plane. Wait. Yeah. So that means the 4 nitrogens. Wait, no, that's 5.
You're looking at just 5. I'm looking at the cobalt being 6 coordinate though. Which structure are you looking at?
the Wikipedia one.
Yeah. What is the coordination number on the cobalt? You must have heard of this term, right? Coordination number.
6 and then octahedral.
Yeah, exactly. Just the standard octahedral, right? Do you also see similarity between this, like the one on the plane, the one in the plane? Do you see the similarity of how it looks like with the hemoglobin and the chlorophyll again?
Yeah, they have the nitrogen carbon ring thing.
It's called a porphyrin, Porphyrin. A lot of things in nature happens to have this as the one of the main backbone. Somehow, I've just given you three examples that all three contains some kind of porphyrin in the, but not every organic metallic complex contains porphyrin. So just to let you know, yeah. Okay, cool.
Yeah.
Going back to that organic stuff just now. So now we have covered into this area called organometallic chemistry. A carbon bonded to a metal, then the polarity you say would be a delta plus on the metal because metals are always electropositive, and delta minus on the carbon. You started with a halogen alkane, which has a carbon halogen bond, halogen being more electronegative than carbon. Therefore, the halogen will be a delta minus, carbon will be a delta plus. So what have you done with just magnesium alone? You have reversed the polarity of the carbon. Do you agree? Okay, draw halogenal alkane. CX delta minus delta plus. Happy?
Yep.
Now what do you have? Now you have a CM. Carbon metal. Happy?
Yeah. Yep.
So what have we done? We have reversed the polarity of carbon. In the first case, the carbon is what you would call, well, it is delta plus. So what feature do you think it will have? Is it nucleophilic at the carbon or electrophilic at the carbon? In the halogenal alkane. Sorry, can you say that again, please?
Nucleophilic at the carbon. Nucleophilic at the carbon.
For which one? For halogenal alkane or for organometallic complexes?
For the halogenal alkane.
When you say nucleophilic at the carbon, nucleophilic at the carbon means the carbon is nucleophilic.
Oh.
Okay. Electrophilic at the carbon means you are electrodeficient at the carbon, and therefore you will be attacked by nucleophile because you are electrophilic. Electrophilic or nucleophilic is the adjective. Okay. So at the carbon halogen bond, the carbon is delta plus. It's actually electrophilic at the carbon, and therefore it will be attacked by nucleophile. Happy?
Yeah.
So what do you think it will do when you have a carbon metal bond?
The carbon is nucleophilic now.
Okay.
And
And you also know that the metal itself likes to they are electropositive, they like to become ions again, right? So this is like a temporary bond. And this is a dative covalent bond where essentially both the electrons come from the carbon because it is essentially a carbon minus and a metal plus. Do you get the idea?
Yep.
And therefore it's nucleophilic at the carbon. Now you have something called CO2. CO2 is non-polar, right? CO2 is non-polar.
Yeah.
CO2 is a linear molecule, right? Okay.
Yep.
But in the CO2 molecule itself, is each of the covalent bond polar or non-polar? The molecule is non-polar, but is the CO bond polar or non-polar?
Polar.
It's polar, right? So what's the
Yeah.
polarity like in a CO bond in a CO2 molecule?
Oxygen delta minus, carbon delta plus.
Okay, cool. So imagine now you have a carbon metal bond, and now you are chucking a carbon dioxide to it. So imagine the carbon being the nucleophile. Where would it attack the carbon dioxide molecule? Would it attack at the carbon or will it attack at the oxygen of the carbon dioxide molecule?
Attack at the carbon because it's
Okay.
carbon delta plus.
Okay. I will just draw you the mechanism. This is how it will look like. So do you see how I draw the arrow not from the carbon but from the bond itself?
Yeah.
And why I attack that carbon? Because I already shown the polarity as a delta plus, and then carbon can only form 4 bonds. So when I form the new bond, then I have to form an O minus. Happy?
Yep.
And then when you have that, then what essentially happened is I haven't drawn the whole complete molecule, but what essentially happened is you have this. So that's the backbone of the molecule which I haven't drawn, but what you have is an O minus, right?
Yeah.
And then what else is in the reaction? You also have acid. Do you see that? So you do it in the presence of acid, carbon dioxide bubble in as a gas in the presence of acid. Then what's gonna happen then? Guess what? You have just formed carboxylic acid.
Yes.
So you have gone from a halogenal alkane, which is CX, and you have made the X into a CO2H.
Yeah.
Okay. How would you do this in school in A level? You unfortunately you don't learn this in A level, so you can't do it. So if I were to ask you to do it in A level, how would you go from a halogenal alkane to a carboxylic acid?
Halogenal alkane to
Such as let's just say CH3, CH2, Cl, and then
CH2 Cl to an
yeah,
acid.
and then you convert the Cl into a CO2H. So now you will have, what will you have? Can you tell me the structural formula? What will you have?
CH3 CH2 COOH.
Yeah, okay. So how would you do that in A level using your knowledge?
Yeah, nucleophilic substitution with CN. So
You mean Cn minus or Cn?
CN minus CN.
Yeah, you need a nucleophilic source, right?
Oh,
Because
we use K plus CN minus, so CN minus.
yeah, okay. And then
And then we would form propanitrile. So
uh-huh.
then from that we just add HCl, the concentrated HCl, and reflux.
What will they do? Do you need concentrated, by the way?
Do we need concentrate?
No, it's just a very simple question. Do you need concentrated?
Yeah, then it would be hydrolysis.
Wait, so what are you doing in the next step? You're converting the Cn to COH, right? What reaction is that called?
Hydrolysis.
But didn't you say like if you use dilute, then it will be hydrolysis? But if you use concentrated, what is it called?
Esterification.
Huh? Is it? Really? But we didn't have OH, right? You had CH3, CH2, Cl, right? Do you get esterification? I don't know. Plus, by the way, that's why we use dilute. HCl, right? We don't even, you can use a dilute H2SO4, it doesn't matter. You're not going to get esterification in this case because you don't have a source of alcohol here.
Yeah.
Yeah? Happy?
Yep.
Okay, so make sure you, seems like you're quite shaky on your normal A level as well, yeah? Okay, make sure you're talking about the right thing. Okay, so what you've done there is a nucleophilic substitution because that carbon is delta plus. What they have done here is what they do in research lab. So they could have asked you in a normal state, you could have gone through that if you don't know about this reaction. But now that they provided you with this reagent, you're supposed to think about how you would react with it. And yeah, now you know. Okay, when you have a metal to the carbon, you reverse the polarity and it's no longer being attacked by Cn minus. You attack the CO2 and then you can just take out an acid and then straight away. Okay, it's one pot by the way because CO2 is a gas and then H plus is a solution, you just add in dilute acid. Whereas in the other step, you have to go to the Cn minus. You have to go through Cn minus, and Cn minus is really toxic to you, yeah? Yeah. Okay, and this step is a lot cleaner. But obviously, by the way, you can't use this in A level, unfortunately.
Yeah.
But to be honest, even if you use this in A level, it's perfectly correct. Yeah. So if they actually don't give you the mark, they're actually terrible chemists because this is very sophisticated chemistry. So can you tell me what compound B is? So just now you got compound A. So can you draw for me compound B? So you are told that there is a very broad infrared thing at 3100 and also a very sharp band at 1716.
Yeah.
So you got A just now, right? Now you know what magnesium does. You know you got B for me. Yep, that's fine. So the next step again, it corresponds to the OH bond being the broad one, and then you also have a carbonyl, right? At the 1700 something. Yeah, the C double bond O carbonyl. It's not the functional group, it's the bond that's responsible for infrared. Yeah, we'll talk about more infrared next time. So again, the SOCO2 will chlorinate any hydroxyl group. So do you want to suggest what compound C is?
Acyl chloride.
Do you want to draw for me?
Yeah. COCl.
Yep, fine. The next one is a bit hard, but it's already been done for you at the bottom there, right? So you started from a ketone, and then this reaction you don't need to know, but essentially what happened is yeah, okay. Essentially what happened is I'll draw you the mechanism and then you might understand. So have a look at that reaction while I draw the mechanism. I have a ketone. So what I've done is I've lost my ketone group and now I form an alkene. So the base there, you have a carboxylic acid, which is the obvious, very, very obvious choice to deprotonate. But for this chemistry to work, it actually doesn't deprotonate there. So I'll show you where it deprotonates. And it's all down to resonance chemistry. So it's like that. Can you see that? Is it clear to you? So I did tell you the carboxylic acid is the most acidic group, but carboxylic acid is only weakly acidic, right? Carboxylic acid is a weak acid.
Yeah.
Yep. This thing there is also acidic. Why is it acidic? Because when you deprotonate that one, that bond can go there and it can get delocalized into the cyanide region. As a matter of fact, you can get delocalized into the carbonyl region as well. So you can stabilize the negative charge and therefore you make it into that group there, into the slightly stronger acidic group.
Yeah. Okay.
And if you had a look at the product, you will see this is the only possibility how the reaction will work. Because if you react at the carbon dioxide, it's not going to give you the product. Okay.
Yeah.
Now I'm going to attack the thing there.
COH and then
Look what I've done. I've reformed the carbon nitrogen triple bond,
yeah.
and then now I've used that thing to act as a nucleophile. So this carbon there stay intact, but this carbon now act as a nucleophile. Is going to form a new bond to this carbon now.
Yeah.
Yeah. And then what I'm going to get is I'm going to get a O. I'm going to get a carbon, a H, a CO2H. I'm going to get this. Oh, sorry. O minus.
Yeah.
Yeah, okay. And then through some proton exchange, because I am also in carboxylic acid region, I also have a base. I will have H plus, I will have OH minus, I have water. Okay? Because
Yeah.
if you have a base, you have H2O. But I'm also in the presence of weak acid, which has H plus, right? So what happened now is what happened now is remember I said just now that this is the more acidic proton. Yeah.
Yeah.
And you have two of them. And guess what? You have another one. You have another one. Can you see that?
Yeah.
Okay. Guess what? You're also in the presence of base. What will the base do? It will do it a second time. But
Yeah.
instead of doing a second time is, what it will do is, I'll just show this in one step. The base go for that acidic proton. Okay.
Okay. Yeah.
Take a look at the product. What do you have? You have formed a carbon-carbon double bond. You have formed an alkene, right?
Yeah.
Yeah.
See
Okay.
that?
I'll show you where the double bond is formed. This is the second step. Do you see what is different just now? So the base attack the proton, and then you form that double bond. Yeah.
Yeah. Yep.
And then guess what? Once you form that double bond, you kick out the OH minus. Can you see that?
Yeah.
Step by step, right? Yeah.
And
Guess what? Now you have your product. You have your alkene, CO2H. Now you have this, which is the production, right?
yeah.
Cool. Anyway, the next part is on you. When you heat it, you got two things. You got a colorless gas with a molar mass of 44, and you also get compound D. First of all, the colorless gas is the easier one to get. So do you want to suggest what the colorless gas could be?
Carbon dioxide.
Okay, because carbon dioxide is quite popular. Even in mass spec, you should know 44 is very important because it's a release of CO2 as a cation plus. Yeah. Okay. Now the next job is, if that is CO2, what is D then? you have to think about. You have to suggest it.
Yeah.
And by the way, if you look at it, compound D gets reduced because LiLH4S reduction. It gets reduced to E. And E plus C, which was acyl chloride plus something form F. So instead of working out D first, I would say maybe you can work out what is E first. E.
Okay.
E for elephant. So you got the acyl chloride just now, right?
Yeah. Yeah.
Yeah. So you know the acyl chloride will react to form F. So F is from acyl chloride plus E. So what is E? Can you draw me E? Hang on, I can't see. So E is going to be that 1, 2. Okay, so what reaction is that to form F? So C plus E form F. What reaction is that?
Condensation reaction.
Okay, so essentially you are kicking out a molecule of water, so that's why it's called condensation. Yeah, they haven't shown it in the balance equation, but there's one molecule of water being kicked out because you are forming what kind of bond there? What kind of functional group are you forming?
An amide bond.
It's an amide bond. So acyl chloride is far more reactive than carboxylic acid. That's why you don't need any heat or reflux. It will
Yeah.
the amine can just attack the acyl chloride easily. So now that you know E is that, and you know that E is formed from D, as a result of reduction and then acidification. Do you want to suggest what D looks like? So you know before D is like that, it lost a CO2 and it will get reduced to form E.
Okay. That means NH2. That's an extra carbon. So that means a nitrile group. Nitrile group in the place of the NH2, and then H plus.
Okay, hang on. Let me have a look. That and that and that and H plus D. Have can you work out the molecular formula for the compound before you get D and X? The molecular formula before you get D, before the heating bit. Just work out the molecular formula.
Molecular formula. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons.
Uh-huh.
And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens.
So how many hydrogen?
12.
Hang on. Oh, yeah, okay. Wait. 2, 10, 11. There's only 11.
Oh, wait. 11.
Yep, okay. Go on.
So C9H11O2N.
Okay. When you lost CO2, which is the colorless gas, what should be the molecular formula for D?
You lose CO2. So C8H11N. C8H11. Yeah, C811H8. C8H11N.
Okay, so have a look at your formula again. Have a look at your formula again, as in the one you draw, and see if that makes sense or not. Did it work out right?
Nope. There's nine carbons.
Okay. I need to look this up as well. Hang on.
15 hydrogens.
Okay, I lost track of what I was gonna do. But yeah, that's the final thing actually. Can you just take a photo and send it to me, and then I'll send the correct compound D to you later on. Your compound E is definitely correct, so we're just left with compound D. I'll send you what compound D later on. Yeah. Okay, cool. We actually passed the 1 hour already. I have to go somewhere, but if you just send me the photo, I'll send you what compound D should be later on. But what have we done today? We know that we can reverse polarity because by applying electronegativity. Yeah, carbon halogen, because halogen is on the other side of the carbon, being more electronegative than carbon. But metals are more electronegative than carbon, therefore you can reverse polarity, and you ended up with these kind of species called organometallic species. And organometallic reagents are very useful because I'll give you two organometallic reagents you can look up yourself. One is called butyl lithium. Butyl lithium.
Okay.
If you type butyl lithium, the first thing that comes on Wikipedia, you can find already what it is. Okay,
Yeah.
it's basically a butyl minus group with a lithium plus. So straight away you can think, carbon minus nucleophilic carbon. The thing is metal minus lithium plus. They both have various uses. including as a strong base. Because if you have a acidic proton, straight away acidic proton will be taken. Okay, but other than this butyl lithium, methyl lithium, magnesium has a very important role. Magnesium has a very important role because someone named Grignard, 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 okay? He's the father of this area because what he does is he chuck magnesium into halogenal alkane. And what he get is you get a, if you basically you can convert any reactive halogenal alkane and reverse the polarity just by chucking it into magnesium. Just by chucking magnesium into it. That's it. It's a very powerful chemistry. You go from electrophilic to nucleophilic.
Yeah.
Okay. The idea is very simple, but obviously you can do a lot of things with it, and everything comes down to just understanding electronegativity and polarity. Yeah. Okay. I will send you this thing on organic synthesis later on. But what we have also done is we identify functional group. You should, well, I mean, you're quite well equipped. You know how to work backward as well when needed to, and you know the reactions that what things are supposed to do. Organic synthesis, there's often more than one way to get to the end. You might have only know limited ways because you're in A level, but they can throw ideas at you, and you're supposed to pick them up quickly as you go along. And if you got questions, feel free to ask. But with any organic reaction, two things. What are the two things? Electronics and steric. They are the two things you need to think about when you think about organic reaction. Electronic is the easiest thing because that's what you have been doing all this time. Rich attack poor. Nucleophile attack electrophile. Negative attacks positive. That's the simple bit. Very simple. Steric is something you might not be familiar with. Steric is why SN2? Why not SN1? Or why SN1? Why not SN2? When you have to attack from behind, but it's being sterically hindered, you can't do it because to do it you have to go through all these things which block your pathway. If you can't do it, therefore you have to go through the other pathway. So steric is very important as well.
Yeah.
Okay, what you draw on paper, you can't see how big it is, but sometimes things are big. Okay,
Yeah.
so steric and electronics, those two are very important. The last thing I want to talk about is when you go back 2 weeks ago, we talked about inductive effect and also resonance effect. Yeah, those come under electronics. Yeah, it's like rich attack poor. We talk about that, right?
Yep.
But poor is poor. How electron deficient is electron deficient? How electron rich is electron rich? They can be affected by two factors. One is inductive factor. One is resonance factor. The resonance factor is the more important one. When you have a nitro group NO2, it's more electron withdrawing than say a fluorine group. Actually, fluorine group is not electron withdrawing because all the halogens, even though they are inductively electron withdrawing, but they are by resonance, they are donating into the aromatic ring. So they're actually auto and para directing, to and directing for that reason, because they're donating into the ring by a stronger electronic effect called resonance. Okay, so there you go. Everything, electronics, steric, those are the two most important things in organic. There's a whole chapter in the Peter Waters and Keeler book. It's just talking about electronics and sterics. You can read about it. Well, they are in the later chapter. You can read about it when you come to it. But yeah, I'll leave it there. I'll send you that structure later on. But have you got any questions in the meantime?
No.
Okay, cool. We'll leave it there. And no work for the next few weeks. Good luck for levels. In the meantime, you should finish off your personal statement. Ask a few people to read at it. I will take one look at it, and then you should ask other people to look at it as well. Yeah.
Okay.
Cool. And hopefully you can get everything sorted out before your exam. And when is your first paper?
24th October actually.
Sorry, what?
The 24th of October.
Are you dropping AS?
Yeah.
Oh, okay. Yeah. So no wonder you started that late. Okay, cool. No worries. But yeah, in the meantime, do all those things. Do TSA. We can do another session next week. You can talk about stuff like this. But yeah, I mean, we'll think about it when the time comes. So no need to prepare ahead of time. Just be yourself. Just know your chemistry in general. Cool.
Okay.
All right. Okay.
Right.
I will stop recording. I will, as usual, put this on the